Hello, everybody, and welcome to our full vehicle simulation for electromagnetic compatibility and electromagnetic environmental effects of structures and cables, an EMA Expo 2025 event. My name is Jason DiMartino, and I'll be your host for today's presentation. It's going to run for about 90 minutes, after which we'll have 30 minutes to go over questions. Please be advised that to submit any questions you have during today's webinar, you can use the Teams webinar Q&A feature. And after the presentation, we'll address any submitted. If there are any unanswered questions at the end of the webinar, we'll address them by email offline. Our speaker today is Megan McGuire. Megan McGuire is a senior scientist at EMA, Electromagnetic Applications. She obtained a Bachelor of Arts in Astronomy with Physics and a BS in Chemical Engineering from the University of Colorado at Boulder. She joined EMA in 2017 and has since focused on generating high-fidelity vehicle models for the simulation and analysis of a variety of electromagnetic environmental environments. Her experience has included the simulation of lightning direct and indirect effects in support of lightning certification, electric field modeling, to aid in assigning lightning zones for novel aircraft, simulation of both low-level swept field and low-level swept current coupling for high-intensity radiated fields, as well as using simulation to assess the threat posed to systems from a high-altitude EMP. Without further delay, I give you Megan.
Hello. Yes, thank you for the introduction. So I'll just start off with a quick overview of basically the questions that this session will aim to answer. So one of the questions is, why simulate a full platform? Is it worth the effort? It takes a lot of time, a lot of modeling effort to create these full vehicle models. Is it worth it? Spoiler alert, yes. Where do you start? So what data do you need at the beginning when you start modeling? And then how do you know that the model that you've created accurately approximates reality, so that you are accurately representing the physical platform? And then what components should be modeled? So do you model everything? Do you model some subset? What sort of simplifications do you make and why? And then finally, what do you do with the results? So how do they correspond with certification standards? Basically taking it from simulation, comparing to test, or like in the case of lightning, assigning like DL160 levels, stuff like that. So first off, EMC tests are very expensive and can only be performed with a physical prototype. So one of the benefits of simulation is you can do a lot of iterations, changing parameters for certain equipment or vehicles, and you don't have to pay for lab time. So that's one of the benefits. Additionally, in a traditional or like a conventional setup, total design changes can happen late in the process, which is extremely expensive. Whereas when you use simulation, you can actually start looking at how different changes impact your vehicle very early on in the process, and therefore it costs a lot less money. So for a full platform, what can it provide? So first off, it can provide confidence going into a test. You have an idea of what to expect, what sort of waveforms that you may see, what sort of levels you might see. And then once you validate a model against testing, you can actually simulate new design changes. So things like material changes, harness changes, changes to bonding and grounding, or even structural changes. And then finally, you can predict in situ coupling to harnesses and equipment. For testing, this isn't really possible because you have to modify the vehicle configuration to allow for internal access, to allow for the placement of antennas, probes, data collection devices. For simulation, you don't have to do that. You can, like for your plane, model it, simulate it, how it would be in flight. Another benefit is a single model can be used across multiple applications. So this is showing a lot of different platforms, but you can actually use a single model for lightning direct and indirect effects, for HERF, LLSC, and LLSF, for EMP. And then also you can use simulation to look at electromagnetic interference and compatibility, EMI, EMC, as well as your mil standard tests, mil standard and DO-160 tests. So I'm going to start with a bit of background on the code, the FDTD code, and then EMC Plus and M-harness. So EMC Plus is a full wave finite difference time domain solver of Maxwell's equations. M-harness, which is what we use for the cables and the harnesses, is a transmission line solver of the telegrapher's equations. Ansys Discovery is the simulation platform on which the geometry is modeled, the material properties are input, simulation parameters are defined. And then EMC Plus with integrated M-harness is what we typically use to solve these EM problems for full aerospace vehicles, from basically like the full vehicle geometry down to the pin interface level. So EMC Plus uses mathematical formulations that allow for the placement of these M-harness cables within the problem space, with the associated, solutions for each solved self-consistently. Cables in M-harness can possess pretty much any radius. You can have very small cables or you can have very large cables. When they're very large, they expand into many different cells. And I'll cover this a bit later, but essentially the cross-sectional size increases and the effective mesh takes up multiple cells. One limitation is that cables cannot overlap with other M-harness cables in this grid, and they also can't overlap with different materials. So the FDTD mesh is made up of these cubic cells. They don't have to be the same size in each dimension, but typically we'll go with similar size in each dimension. So they're just cubes. Electric fields are calculated on the lattice edges. And so you can see that here, the red arrows, that's where electric fields are calculated. Magnetic fields are calculated on the lattice faces, so those would be the blue arrows here. This has some implications for probe placement, which I'll get into a bit later. And then also finally, this is just an example of what the FDTD mesh looks like relative to the original geometry. So you can see that for things that have a lot of curvature, you'll want to use like a smaller mesh cell size in order to resolve those details if that's needed. So in terms of complex cable modeling, so EMC Plus with M-harness can be used to represent pretty much any harness configuration that you want for your vehicle. So you can have any number of shields, pins, you can have standard cables that come with the software. So like we have a library of cables that you can include, or you can create your own custom cables. And then finally, there's also the option for Nexum circuit terminations. So you can have complex circuit terminations for your cables. And at the bottom, this is just an example of how you can start with a wire harness and diagram with the CATIA 3D modeling, and then have your center line representation within your model here with this cross-section in M-harness. So in the model itself, it looks like a line, but M-harness allows for very complex cross-sections within that harness. So just a quick overview of M-harness. So as I said previously, you can have any combination of pins, shields, and braids, as well as your own custom cables. You can control properties such as the transfer resistance and transfer inductance, as well as the shape, radius, jacket insulation, or filler materials. And then also cable placement within the harness can be controlled by the user. So we have a feature where you can actually move around cables within the harness to control that, or you can have it automatically pack the cables. There are also a lot of different termination options available. On this slide, I show just a couple of them where you can say you want to join the pins when in a TSP at one end, you have that option. You can have cable splices. So you can have, let's say, 2 pins that then connect to another pin. So you have that junction. You can stop an overbraid short or a shield short and have the wire continue on unshielded. There are a lot of different ways that you can do this within the software, but these are just a few examples. And then in terms of cable shielding options, you have the option to define or to select a transfer inductance analytical model, and you can input things like the carrier number, the weave angle, and have it calculate your transfer impedance parameters. Alternatively, there are options, or there is the option of using library overbraids. So we have collaborated with Glen Eyre to provide overbraids with measured values that then you can just input into the model. So some of the ones included are silver-plated copper braids, armor light, master wrap, and amber strands. And then on the right, I just show some snapshots from the UI of what this option looks like. So the upper left is for the transfer inductance. Here we've said that we want an analytical method with advanced analytical model, and then you input details such as the strand radius, conductivity, strand count, carrier count, weave angle. And then on the bottom here is an image of the library where you can say you want to select the Glen Air cable, armor light microfilament braid, and then you can select the size that you would like. Now getting into the actual modeling details. And so a lot of the examples are for an aircraft model. This does extend to other vehicles, but for this section, a lot of the images will come from an aircraft. So this is kind of the overall view of what I'm going to be covering. So I'll start with basic modeling approach. So what things that you want to take into account. And then I'll move into CAD pre-processing. This is your CAD cleaning stage, your geometry simplification. Then defining the domain. So basically what your domain size is, boundary conditions for the domain, things like that. And then I'm going to address some considerations for low frequency problems. And then assigning materials. So what things you want to keep track of for isotropic materials, if you want to include anisotropic materials. After that, I'm going to talk about defining seams and joints. So that would be like, panel-to-panel bonding, things like that, as well as some kind of gotchas and things to consider when making those definitions. Then I'll cover some a bit about how to define cables and some considerations for that as well. Then I'll move into talking about selecting a source. So what you do for, say, a lightning source versus a HERF source. Defining probes, as well as some of the gotchas there that have to do with how probes interface with the mesh. And then finally, some processing of results. Following that, I'll give some general guidance for lightning and HERF that kind of apply those that process to those, and then give some details about typical parameters you may want to use in your simulations. So starting off with the modeling approach. So there are 4 primary stages to computational electromagnetic modeling, or CEM modeling. So you want to start with your problem definition and develop a plan. So what do you want to simulate? What probes do you want to use to achieve this? And where do those probes need to be placed? Then you move into pre-processing. So this is where you start with your manufacturing CAD, and then you basically simplify it into a suitable electromagnetic model. You mesh that model, you make sure your mesh looks good. You prepare your model, or so you prepare your model with material assignments. And then after that, you move into the solver phase. So this is when you're just running the simulation. So for EMA 3D and M harness, you use an FDTD mesh and solver, in this case, solving Maxwell's equations, and then outputting field data or current data based on the probes you select. And then that data can then be processed in Discovery, or for more advanced methods, you may choose to use MATLAB or Python to make plots and animations. And then lastly, sometimes, depending on where you are at in the process for your program, you may be to the point where you want to do validation or establish simulation accuracy or margins. So for simulation preparation, there are several different types of analyses you can use to learn about your platform. Those are a conservative approach, a predictive approach, or sensitivity analysis. For the conservative analysis, you want to set up your simulation such that it will provide high-end or worst-case estimates for transients. You can use this to kind of bound your problem. So what would be the worst thing that you'd see? In this case, maybe you'd be using a very severe environment that you may not otherwise see, or you can be using open circuit voltage, short circuit current, things like that, or very poor bonding. For predictive analysis, you want to represent the aircraft and harnesses with high fidelity and how they would be represented, say, in like testing or in actual flight. And then lastly, sensitivity analysis. So this would kind of be a combination of the previous two, where you can look at the very severe end, or you can look at what if we have ideal bonding, and kind of try to create a range of data, and then also kind of look at specific areas and see how those parameters impact your overall transients. So the correct simulation approach needs to balance accuracy as well as the amount of time that you have to create this model and run it, and the amount of information you have. Like, you may not have enough information to create a very high fidelity model, or you may not have enough time. It can take a long time to create these vehicles. Say if you want to include most of your harnesses, that's going to take an extremely long time that you may not have. And so one of the things that you may look at is where can you simplify. But every model requires these sorts of assumptions. So not every parameter can be characterized with test. And so you'll have to make assumptions. Not every harness can be modeled. So you have to figure out which ones you need to include. But you can use small physical tests to help characterize important parameters for the model and use those as inputs. So this is kind of like two different types of models on the bottom here. So you have your canonical or submodels where you can do parameter studies. You can design feature characterization, and you can focus on certain areas. For high fidelity models, that's when you get into the full vehicle coupling. So you can see like the larger picture. These are helpful in certification support because they can also provide high accuracy results. And then this is just a visual of the different scales for simulation. So starting at the bottom, moving to the top, it's increasing fidelity and complexity, as well as increasing cost for test and manufacturing. So you can simulate elementary test articles, so very small samples, so like in this case, 2 small panels, or you can go up to a larger section, so small scale test articles, onto medium scale test articles, so say a wing box or a fuel tank. And then finally, you have your large scale test articles, which would be your full vehicles, so like your full airplane, or in this case, it's showing a subset of an airplane, but those are some options. So for a particular aircraft simulation, or really most simulations, you need to define what components to include. That's one of the first things that you'll be doing. And then you want to research parameters. So you want to figure out what sort of conductivities and resistivities need to be used for materials, as well as seam impedances. Then you need to decide on the source. So for lightning, you need to define an attach and detach location. And for most analyses, you'll want to have several of these. Because you have multiple, zone 1A areas for an aircraft, you want to look at multiple different scenarios of attach and detach. For HERF and EMP, you'll want to select the environment level, or you may be going with the general one and looking at transfer functions. But you also want to select a plane wave orientation and polarization. And for these, you'll want to do several different illuminations. Next, you want to determine your probes. So are you looking at structural currents and voltages? For example, are you doing a direct effects simulation? If you're doing indirect effects, you want to probe harness and wire currents and voltages. And then also, depending on your simulation, you may want to look at electric and magnetic fields, as well as animations for those. And then lastly, you want to decide if any special features need to be used for the simulations, or if it's more of a standard model. So steps for building the model. So first you import your CAD geometry, and then you simplify it or defeature it. You mesh and check the mesh connectivity. You determine your material properties, so your structural material properties, cable transfer impedances, and seam and joint impedances. Those 3 can be measured at the same time as when the model is being developed, and then those values can later be updated. You want to then route and define cable harnesses. I tend to do this later in the model development stage, just because you have to keep in mind how the mesh of those interacts with the mesh of the structures. And then lastly, you want to define your probes before simulating your environment. So CAD preprocessing, what does this mean? Simulation models can't use all the information that you have in manufacturing CAD. It's extremely large in terms of required memory or file size. And then also, it can be incredibly challenging to control your mesh. And your mesh is your fundamental, the fundamental part of your simulation. So that's what you're using to represent it. So if you can't control your mesh, you're not going to have a high fidelity simulation, essentially. In doing so, you want to make sure that you're still capturing the important electromagnetic features of your platform. So for structures, you want to make sure that you're getting the right shape and size for inductive purposes. And then you also want to make sure that you are including the correct materials for resistance purposes. The most common way of simplifying that we do is taking the original bodies and then simplifying them to representative surfaces in the model. And we found this to be an effective method of representing these 3D structures. So at the bottom here, this is just the original CAD that you may see, and then what it looks like when it's simplified down to surfaces. So you can see you're still representing the structures accurately in terms of their size and with the materials when you put it in, but it's a much more pared down version. So as an example, this is a rib at the top left that you may receive or that you may have in the original CATIA data. And so it has a lot of points, lines, surfaces. So like it has fastener holes, it has a lot of features. What you'll do for simplifying it is basically just getting a surface that represents it. So you may be able to copy your surface from the body or split the body with a plane from one of these sections of the rib. But ultimately, it's a much more simplified shape that then is easier to work with the mesh for seams and joints. And then also, once again, the size of the model overall. So this is just kind of a view of a simplified version, or yeah, a simplified model for a general airplane. So it's showing that things like the skin, the wings are all have representative surface definitions, as well as things like the interior floor. For cables, you want to represent them with the center line of the harness. So kind of zooming in, you can see that what you may receive or what you may have is that larger sort of harness representation. You'll want to generate center lines, and those lines are what you'll use to then later define your cable inputs. So next, defining the domain. So this is the first step in setting up your model. So there's 4 different things, or 4 different steps in defining your domain. So you have your time steps. So defining your step size, end time, time increment method, as well, or your frequency range of interest. The next is the lattice. So your problem space size. How much buffer room do you need from geometry to your edges? It depends on the type of problem. I'll cover that a bit later when I go over the lightning and HERF. Boundaries, so these would be the boundary conditions on the 6 different domain faces. Depending on your problem, you may use different boundary conditions. And then lastly, there's the background, which is the background electromagnetic problems, or background electromagnetic properties of your model. So the default is just vacuum or air, but you can change that property to have the whole domain be some other material. So for the time section of the domain, you can either define your frequency range of interest, or you can define the time parameters, so your time step and end time. They're interdependent, so changing one will change the other for frequency versus time. One thing to keep in mind for your time, your end time for your simulation is you want to have that your end time be 1 decade lower than your frequency, or you want your end time to be 1 decade lower than your lowest frequency of interest. So, and it's like essentially your simulation is going to be 10 times longer, and that's so that you can get enough data at that lower frequency, like enough data points to have useful information. So the time step size is calculated from a combination of your highest frequency of interest and the lattice step size, as well as the stability margin. So the highest frequency that you can resolve in your model is dependent on your lattice step size, so your mesh cell size. You need a minimum of 10 FDTD cells per wavelength at the highest frequency. For some cases, this may need to be increased, but the minimum is 10. The maximum allowable time step size is called the Courant condition. Above that, numerical instability will manifest, and this time step size is the amount of time it would take light to traverse the long side of a cell, essentially. And then the stability margin is just used to essentially reduce this time step lower than the Courant condition. So the higher your stability margin, the more likely your simulation is to be stable, essentially. So if you're having stability issues, decreasing your time step is generally one of the first things you'll look into doing. I'd recommend at least 15% for stability margin. I tend to use about 20. But yeah, so for simulations containing dielectric materials or complex harnesses, you'll likely need to decrease your time step or increase your stability margin. In cases where numerical instability may be likely, the solver will actually output a warning indicating this and provide the user with a recommended time step. So it's not something that you'll need to really guess at, which is nice. The increment method is basically what it says is how does the time step increment. So you can use constant, so the time step size will be the same throughout the entire simulation. This is recommended for most problem types. However, there's also the option for magnetostatic stepping or increment method, where you can define time steps over which an exponential ramp is applied to the permittivity values, and this allows for an increase in time step size over time. This is only valid in cases of for low frequency problems, so ones that are magnetostatic or quasi-magnetostatic, such as lightning. Moving on to the lattice part, so the minimum and maximum locations for the lattice can be defined. The step size corresponds to the mesh cell size, and the number of divisions, when it says that, is the number of divisions used for processors and parallel computation. As I mentioned before, you want to have at least 10 cells per wavelength at your highest frequency or your smallest wavelength. For very high frequency problems, you may want to increase the number of cells to 15 or 20, maybe even higher. So boundary conditions, there are 6 sides to your domain, and these can each have an individual boundary condition applied, with the exception of periodic and PML boundary conditions. Those do have some restrictions. The type of boundary condition you want to use depends on the type of problem you're looking at. So if you're looking at a metallic enclosure or something over a metallic ground plane, you may use a PEC boundary. If you're looking at electromagnetic responses in open air, then PML boundaries may be used. So that would be for something like HERF or EMP. If your problem requires geometry to intersect the boundary, but you still want it to be absorbing like PML, you would want to use something like MER1H field, or HMER is another thing that it's called. That allows things like a lightning source to go to the boundary or a PEC detach line. This would not be allowed with PML. So low frequency problems like lightning. So these involve a few extra steps in the model. Well, I say steps, it doesn't actually require a lot of time to do these, but they are additional considerations when setting up your model. So there's the M-harness low frequency approximation, and then there's the magnetostatic scaling that I mentioned earlier. So at low frequencies, cable shields can become somewhat transparent. So what you'll want to do is, in order to accurately represent this, what's going on in this case, you want to go into your harness settings in M-harness and check the low frequency approximation. So this allows electromagnetic energy to couple accurately to the interior conductors. Without that, it may not, or it will not accurately couple. So, however, for high frequency problems, don't use this approximation. So really, pretty much lightning is one of the few applications where it would be used. Magnetostatic scaling, you might also hear this, like if you're talking to people, they may call it epsilon scaling or permittivity scaling. It's one of the increment methods in the time section of the domain menu. It should only be used at low frequencies, such as lightning, so magnetostatic or quasi-magnetostatic problems. And the reason being that in these cases, the displacement current becomes very small. And so the impact that permittivity or relative permittivity has on the electromagnetic behavior of your problem is minimal. And by changing this value, you can change this speed of propagation of light in your domain, and therefore increase your time step based on the increasing Courant condition limit. The benefit of using this feature is I think it's pretty clear. In increasing time step, your simulation is going to run faster. And it actually can have a very significant time or a very significant impact in the computation time. So some examples as for what good values would be, I tend to have success when I use, so for my first definition, 10 time steps is when I start the magnetostatic scaling, and then I'll have it go up to a factor of 1,000 at 50 microseconds. This factor is the multiplier on your permittivity value. And then have it go to the end from 50 microseconds to like 500 microseconds, going up to 10,000 for the factor. In each of those sections, you have an exponential rate of change for your epsilon multiplier. So like, let's say at 40 nanoseconds, it starts at 1 times your epsilon value. At 50 microseconds, it'll be at 1,000 times your initial epsilon value, but that ramp between occurs exponentially. More conservative magnetostatic scaling would be, say, not starting your ramping until 6 microseconds in. And then more aggressive would be maybe having your first ramp go from the first 10 microseconds up to 30, the first 10 time steps up to 30 microseconds. It can be kind of difficult to figure out what magnetostatic scaling parameters are good for your simulation. So these are just ones that I tend to recommend as starting points. So some possible issues that you can have with magnetostatic scaling would be inaccurate or low amplitudes. So if you're too aggressive with your magnetostatic scaling, you can artificially change the amplitude of your signals. One way to check for this is looking at your attach and detach waveforms, say for lightning. If your detached waveform is a lower amplitude by, like, say 95% of your source, your magnetostatic scaling is probably too aggressive, so you'll want to ease back on that. Another thing that you might see are trumpeting oscillations or increasing oscillations over time, which you can kind of see on the right here. These can be caused by magnetostatic scaling, where it's introducing noise. However, they don't necessarily mean that your simulation isn't good. So if you can make out a waveform and it's only, and these oscillations are really constrained to later times, then it may be that the model is deemed or like the simulation is deemed acceptable. So as you can see, it can be kind of difficult to select the right scaling parameters. Some models might be more sensitive to the rate of change of permittivity than others. What might work for one model might not work for another. Frequently, what you'll need to do at the beginning is just run a couple test simulations with different parameters to see what works best. So assigning materials. I'll start with isotropic materials. So they're a very common type of material to assign to surfaces or non-harness lines. So you can define the name of your material, the display color, as well as the electromagnetic properties. For most models, the actual thickness of a material won't match your model cell size. The model cell size is the effective thickness of a surface in your model. So let's say your model cell size is 25 millimeters. That surface, even though it doesn't look like it has thickness in your model, will be seen as 25 millimeters thick. So what you want to do is essentially modify your parameters that you input into the model to account for this. And in doing so, so basically the calculation is you want the actual resistance to be the same as the model resistance. And so you can achieve this by scaling your model conductivity, or sorry, scaling your actual conductivity by the ratio of the actual thickness of your surface by the model cell size. And this would be your simulation conductivity that you then input for the material. So why is the thickness of a surface one cell size? So essentially what the solver is seeing is the thickness goes from 1/2 cell up above the surface and 1/2 cell below. And so what it looks like for the fields values associated with that surface, they're constrained to just the planar part of that, or just like the planar part of the mesh for your surface. However, the thickness that it sees kind of extends beyond that. So one thing that you may wonder is, what if I have two surfaces that are one cell apart? Like, if the thickness of that surface essentially extends one half cell below, and then for the bottom surface, one half cell above, will there be a connection? The answer is no. As I show here, the field vectors associated with this mesh are only in plane. So you don't have the vertical components between these two surfaces, and therefore they won't have an electrical connection. So essentially saying current won't flow out of plane for these surfaces. So similar to isotropic surfaces, isotropic bodies only include E-field components that are on the mesh cell edges or faces. So depending on your E-field or H-field, one thing to keep in mind is the effective thickness of your body will be equal to the number of cells that you see in your mesh plus one. So let's say you have a 10 millimeter mesh size and you have a 30 millimeter thick panel or something. So you mesh that, you have 3 cells in that thickness for the panel, but what the solver will actually see will be your 10 times 3 millimeters, so 30 millimeters for the thickness, plus half a cell above and below, so plus 10. So the solver will actually see a 40 millimeter thick body. And so that's one thing to keep in mind when you're doing body meshes is, in that case, you would want to have it only be 20 millimeters thick in your model to have it be actually 30 millimeters thick for what the solver sees. So isotropic versus anisotropic materials. CFRP, so carbon fiber reinforced plastic, or sorry, carbon fiber reinforced polymer, and ECF, which is expanded copper foil, materials are anisotropic in nature. The EMC Plus can technically model these anisotropic materials with anisotropic conductivity tensors associated with the different directions, but this can be difficult to control when your geometry has a lot of curvature or they have like a staircase mesh. But locally, anisotropic effects can be important. So if you're working on submodels, you will likely want to take this into account. However, for a lot of CFRP panels, if they have like woven fibers or mixed orientations, the panel can behave isotropically. So typically what you may be able to do for CFRP is go with an isotropic material. For ECF, what you can do, or what's commonly done, is you take your resistance for your long and short directions and average them and use those as a good engineering approximation for an isotropic input. So for your composite panels, kind of said this before, but you have multiple plies that are conductive mainly in the direction of the carbon fibers. So cross fiber conductivity can be extremely low. But if your plies are in different directions, you have the benefit of basically being able to assume an isotropic conductivity. The bulk conductivity of CFRP, though, will vary on the number of plies and the orientations. Typically, a good value to assume, if you don't know, would be, say, 1 e to the 4 Siemens per meter, but it may actually be as high as 5 e to the 5 Siemens per meter. But this is something that you'd probably want to test as an input for your model. For ECF, just as some background, so typically it's a diamond-shaped pattern, so the resistance and direction will be different, so your long direction versus your short direction. The conductivity of copper, while very high, so even though the conductivity of copper is very high, ECF is extremely thin. So the bulk resistivity will be on the order of, like, say, 0.1 to 20 milliohms per square, depending on your orientation. What that means is the bulk conductivity of CFRP and ECF are actually not that different. One thing that you'll want to look for is manufacturing specs to help you figure out what sort of resistance values to use. So one question you might have is, how do you model CFRP and ECF as a stack up? That you can technically model or represent the individual layers. However, that's not practical if you're looking at like a full vehicle model. You'd be looking at an extremely small cell size. Typically, there are multiple fasteners that penetrate the layers of the CFRP and the ECF, and so you can assume that they are essentially you can assume that, or you can represent them with a single surface with a parallel resistance calculation. So assume that they're well connected electrically, and then do a parallel resistance calculation for your CFRP in parallel with your ECF. And then that would be the resistance that, or sorry, not the resistance, but like the conductivity that you then put into the model for a surface, a single surface with that representation of the stack up. And I'll go over an example for this. So you can have two different approaches with the same answer. So like, say for CFRP, you know the panel resistance in ohms per square. Then what you'll do is you'll do 1 over your panel resistance times your model cell size to get your conductivity for your model. The second approach would be if your conductivity is known. And this is what I showed earlier, where it's an adjustment on the actual conductivity by the ratio of your the thickness of the surface and the to the model cell size. So total model conductivity for a single surface, if you have different materials, like materials with different conductivities that are in parallel, would be the sum of your model resistance. In this case, like the model resistance for CFRP and the model resistance for ECF. So that sum would then give you the sum that you would use for your surface. So with actual numbers, let's say we have a wing that is CFRP with ECF. Our model cell size is 25 millimeters. And remembering that the effective surface thickness seen by the solver for this surface is that cell size, so 25 millimeters. So there's two different approaches, as we mentioned before. Let's say you have a 10 millimeter panel that's 10 milliohms per square resistance. Or you can say in bulk, or you can say your bulk resistivity of the CFRP is 1 × 4 Siemens per meter. You then use the 10 millimeter thickness to scale this value. So on the bottom here, you have your 1 over your 10 milliohms per square, 25 millimeter thickness for the actual, 25 millimeter cell size to get 4 × 3 Siemens per meter for your model conductivity for the CFRP. Alternatively, if you have that actual resistance of 1 × 4 Siemens per meter for your CFRP, you'd scale it by the ratio of the thickness, the 10 millimeter thickness of your wing skin by your cell size to get the same number, 4 × 3 Siemens per meter. For ECF, if you assume something like a 3M AF536, your long direction resistance would be 1.6 milliohms per square. Short direction would be 3.2 milliohms per square. You just average that to get 2.4 milliohms per square, and then do that resistance calculation, like option. So 1 over your 2.4 milliohms times your 25 millimeter cell size to get 1.67 e⁴ Siemens per meter. And then adding those together, you get your model conductivity for your single surface representation of the wing of 2.07 e⁴ Siemens per meter. So seams and joints. Seam impedance can have a very big impact on coupling in your model or in your simulation as well as in real life. Seams typically have a lot of different features. They can get quite complex. These can be represented or resolved within the model, but that can take a lot of development time, computation time. It can be rather prohibitive. So what we have is a seam and joint feature that allows you to define the joint as a single line, essentially, using RLC parameters. And so you simplify all of that detail into one input. Sometimes they're also called Berry articles, in case you're talking to someone and they say that. How they work is the input parameters, as you can see on the bottom here, resistance, capacitance, and inductance, are added on top of the existing material property. So they're not a replacement for what's there, it's an addition. As an example, for barrier type of line, you select a surface onto which you want that property applied. And then you select the line along which that property exists, and property being your seam impedance. You then can mesh that, and you can see where that seam impedance is being applied. So on the left here, I show that I selected this left surface as my surface on which I want that impedance to be applied. The red line is the line along which, so you can actually do part of a surface. If you like split if you split the edge for the surface, you can then select part of the surface and not apply it to all of it. So that's one of the considerations there. When you mesh it, you can actually see these lines. I call them action lines. They are basically where that material is being modified with the seam impedance that you've input. So in terms of the type of, or how you can define these, you can have an absolute impedance type or a density impedance type. The absolute impedance type would be input in units of like ohms, farads, and henries. Density is like ohm meters, farad meters, or henry meters. One thing that I like to call out is that density impedance is not in units of per meter. So it's in ohm meter. So given a fixed impedance density, as the length of your seam increases, the total impedance of the seam will decrease. So you can think of it as impedance density is the total impedance of a 1 meter section of the seam. So that's just one thing to keep in mind. One issue that you can run into with seams related to your mesh is a mesh leak. And these can be easy to miss, but can have a big impact on your model. And so when I say mesh leak, I basically mean that current can flow through your model while bypassing a seam. Even though you see the seam being there, it may be bypassing it. And this has to do with basically how things mesh together. So on the bottom, I show an example of this. I have a rib that's blue here going to skin that's red. I select the blue rib to apply the seam to, and then the cyan or greenish line is the line I selected for where it should be applied. The yellow lines are those meshed action lines that it's being applied, or it is how it's modifying the material. So you look at it from the front, it seems fine. But if you look at it from the back, you can see that actually it's not. So based on the mesh, there's some overlap in the skin mesh and the rib mesh that allows current to flow from the rib onto the skin without having to go through one of those action lines. So that's one of the things that you want to keep in mind is just because you apply a seam doesn't necessarily mean that the mesh is working out how you want it to. Another thing you may want to do is individual fastener representations along a joint that has a seam definition. So in this case, you may choose to have two different seams. So your interfastener seam and then a seam for your fastener. One thing I want to call out is possible issues with this approach. So on the left, you can see that I have this blue definition where I have one cell in the middle that I leave out of my interfastener seam definition. And then I make a fastener seam definition at that one cell. Once you combine them, they're overlapping, essentially. You don't know which one's going to end up applying because ultimately, I don't get into the simulation model files, but the EMA file is the one that you run for EMC Plus. Which one takes priority is basically how it's output to the file in order. So if your fastener seam is output to the file later, that's the one that will be used. But if your interfastener seam is output later, that's the one that'll be used. And so it'll be overriding your fastener seam and you won't be representing it. So one way to actually avoid this would be having your seam stop one cell, instead of like having it be one cell, have it be two cells for your interfastener seam where it stops. And then you can put an isotropic line on that one lattice point where your seam action lines don't exist, and then giving your fastener properties to that line. Binding cables. So what's unique about EMC Plus is being able to model in like a full vehicle in terms of structures, but also be able to model cables down to the pin level. And then you can collect data like bundle currents, short circuit current, pin voltages, and I guess I'll go into a bit of how this is done first, and then I'll go do some more details. So in this video, we'll hide the outer structure initially to have a better view of the cable routing. and the internal bulkheads. So then zooming in, go to your M harness tab, you can actually inspect existing harnesses to see what sort of cables exist in those lines. And that can be helpful for seeing branching or seeing what you've already modeled or just creating images of cross sections. Then next, let's say you have an existing overbraid in your model, but you want to add a TSP under it. So you can go right click, say add shield, that overbraid, and then you can go into the library, and then you can select from the general TSP tab and then choose like a 24 gauge TSP shield. And then you select the lines in which you want that shield to be routed. And for areas where your overbraid exists, the shield will be placed under your overbraid. For lines where your overbraid is not routed, the shield will break out of the overbraid, essentially. So it doesn't have to follow the overbraid routing. Then you'll select your termination points. So the beginning and the end, and then also we have a bulkhead in the middle where we want to have the shield connect. So then once that shield is created, you want to add some, or well, you can rename it to what you want, and then you can add some pins underneath that. So in this case, we have a TSP, so we'll want to do 2 conductors. So we'll start with 1 conductor definition, go to the library, and then select a 24 gauge bare wire. And then select the lines in which that wire routes. So in this case, the same lines as the shield that we defined. It's going out to the empennage. And then selecting your termination points, in this case, the beginning and the end, and not selecting that bulkhead because we do not want the pin to connect there. And then you can copy the definition for that for your second pin. So you don't have to redefine each individual. So then you can inspect a single segment. You can see where your TSP is located in that cross section. And then there is an interaction point tool that you can use. So for things like circuit terminations, you can find custom junctions or probes at those locations. You can also go into bulk edit terminations. So in this case, you can look at everything that terminates at that point. And then in our case, we want to change the TSP termination resistance to 2.5 milliohms, and then the conductor resistances as well. You can define these termination resistances when you initially create the conductors, but this is a good way to do so all at once. So then at this bulkhead junction where we wanted the TSP to connect, you can go to your TSP and then select the resistance that it will have to its reference. I'll go over that in a bit. And then lastly, you can bulk edit terminations at the other end for your for your shield and for your pins. So that's kind of a quick overview of creating a custom cable, assigning terminations, viewing cross-sectional, viewing cross-sections. Okay, so large cable bundles. When you have a lot of cables in your route, it can create what's called expanded cables. And what this means is basically the mesh of your cable expands into multiple cells. So under a certain point, it's a subcell representation. The mesh will be the same as the line that you see, or like what the solver sees will be the same. It won't take up multiple cells, essentially. It's on those lattice points for your mesh. However, when it expands into other, like multiple cells, it's actually taking up those FDTD body cells. And what's complicated with that is it can be very difficult to route these expanded cables in structure because I mentioned earlier, you can't have cables exist, like you can't have overlapping mesh for different cable lines, but you also can't have your cable mesh overlap structures or structural materials. So you can think like maybe in a wingtip, having a very large bundle can be rather problematic for routing. And I'll get into kind of some things that you can do to try to reduce the size of these bundles, which is really only applicable in low frequency environments. So like in a lightning environment, transients on cables are well shielded, and also transients are primarily resistively driven rather than inductively driven. And so what you can do is when it's resistively driven, let's say you have 20 TSPs that are all identical routing, identical size, so identical properties. You could model all 20 TSPs. You'd probably have an expanded cable. You're not really going to be getting more information from that than you would get from a single TSP. You can actually take 19 of those, and this is just one method you can use, but you can take 19 of those and combine them into a single representative conductor, essentially. So I give an example with numbers here. So if you have 20 12-gauge TSPs, you'd model one of the TSPs with the actual parameters, and then for the remaining 19, you'd represent them with a single wire with a resistance equal to 19 parallel 12-gauge TSP shields. So you'd be getting, you'd be probing your TSP that you actually represented, and then you'd have those 19 represented in a wire that would account for the additional current paths that those 19 cables would apply. So you're not reducing essentially how much current can be going through that area, if that makes sense. And then also, let's say you have an extremely large pin, like an aught gauge pin. Once again, if it's resistively driven, not inductively driven for your problem, you could reduce the size of that cable to something like, say, a 12-gauge pin, but maintain the original resistance. So these are a couple ways that you can try to keep from having expanded cables in your model, or cut down on the number of cables you're modeling. Like, you want to represent 20 cables to get the proper, or the 20 TSPs to get your proper current distribution, but it takes time to input cables. You can start getting very big models. So even if it's not a case of issues with expanded cables, doing this can be helpful for representing current paths without having to explicitly model hundreds of cables. So boundary conditions. Commonly, 2.5 milliohms is the requirement for like a shield to connector or connector to equipment bonds. So the total resistance from the cable shield to equipment can vary, but 2.5 milliohms is a good value to use when simulating or when modeling. The termination, configuration, and reference conductors should be considered when you're applying these boundary conditions. On the right, I show an example of a TSP with like an overbraid, and then the pins inside are black, the shield is red, and the overbraid is yellow. So you can see in the stack up, that's how it matches up. For the pins, their reference conductor is the shield. So when you apply a boundary condition, I'm just going to stick with like referring to them as resistive for simplicity's sake. But let's say you apply a resistive boundary condition on one of the pins. That'll be the resistance from the pin to its shield. And then the resistance that you apply at the end of the shield will be the resistance from the shield to the braid. And then the resistance that you apply to the braid would be the resistance to its reference, which is either ground if you have a just an M-harness simulation, or it'd be whatever structure it's terminating into if you have an EMC Plus simulation with M-harness. So what this means is if you want your total termination resistance to be 2.5 milliohms, then for that shield, you would want to short it to your braid and then have the braid have a 2.5 milliohm termination resistance to structure. If you have just a shield, no braid, then you do 20 or 2.5 milliohms on the shield. That's just one thing to keep in mind. But yeah, I just wanted to also make it clear that the resistance that you input at your termination is not the conductor to the EMC Plus material necessarily. It's the conductor to its reference. So the two most common cable pin configurations for lightning would be open circuit voltage or short circuit current. These are ones that are used for testing. Open circuit voltage, you're looking for worst case pin voltage transients. Short circuit current, you're looking for worst case pin current transients. Open circuit voltage is pretty straightforward for modeling. However, short circuit current can be a little more complicated. So yeah, so ideally they're simulated separately. This get into why that might not always be the case. So for short circuit current, ideally you'd only be shorting a single pin per injection. So like for testing, you short a single pin and then do another injection with a different pin shorted. For simulation, that's not really feasible, especially if your simulations take days to run. So what can you do in this case? Because if you need short circuit pin current, you can't run dozens of simulations or hundreds of simulations. One approach is selecting a small subset of pins to short at once. So you want to look at pins that will cover a variety of routes or cable lengths. So if you have a bunch of cables that say go from the cockpit to the empennage, even though they go from like maybe different boxes, just choosing one of those and saying I'll short this, and then assume that the other cables would have a similar transient. So it is an approximation. Another less conservative approach would be to short one pin per cable for every cable. So let's say you have a twisted shielded triple, have two of the pins open circuit and have one pin shorted. So this is obviously less conservative because you're introducing a lot more current paths. But it's also on the front end much easier to implement when you're generating your model, because it's basically you just do it for each cable. You're not having to figure out what would be the ideal cables for this. But what you can do essentially is like sometimes you can also combine your short circuit current with your VOC simulations or your open circuit voltage simulations. Say if you're only shorting a few and you anticipate that that would have minimal impact on your open circuit voltages. So this is looking at ways to try to reduce the total number of simulations to run. Bundle currents, I recommend that people probe bundle currents at every connector in the model. So at LRUs, at bulkhead connections, basically to get an overall view of how current is distributing. And then another thing I recommend is, especially at LRU locations, probing bundle current 2 inches away from a connector. The reason being, for lightning, it doesn't matter where you measure your bundle current, but for HERF, typically it's measured at 2 inches from your connector. And so if you create your model with that in mind, you can kind of future-proof it. So say you have your lightning model, you want to eventually use it for HERF, it's already set up to run your HERF simulation without having to move your probes to be 2 inches away. So selecting your source. Plane wave sources are used for simulations like HERF or HEMP, which is high altitude EMP, or shielding effectiveness simulations. Your source, so like when your source, like in these cases, is located a large distance from the vehicle, that the incident field from that source can be reasonably approximated with the plane wave. This plane wave is driven by a surface current distribution across a Huygens surface in the model. That Huygens surface is, it limits basically your domain, and that you need at least 3 cells from your domain boundary to your material. Otherwise, you'll have material intersecting that Huygens surface, which will cause instability or cause issues with your results. On the right, I just show what it looks like when you're setting this up. You can turn on the names for your vectors. So your yellow vector would be your E fields, H fields blue, and then the propagation. And you can define your propagation angles and or polarization angles, some combination of those. Or you can also drag these arrows here to try to do so manually. Another common source is current excitation source. This is what you would use for lightning. So you apply it to some geometry in the model. It can be applied to a line or a surface. For lightning, it's applied to a line that goes from the boundary to your attached location. For that case, you would select an electric current source. And then also you can define the direction of that current. You can see it in the model when you have your current shown with the arrows showing the direction. Defining probes. So starting with field probes, I'll go through just a subset of these. The boxed region field probe is where you can define a region in which you probe electric or magnetic fields at a certain number of points. And what it'll do, it'll probe the components, output the components. The max samples option is where you can limit the number of sample points. So you may not want to sample the field at every lattice point in your box, especially for larger boxes. So by setting this limit, you can reduce how many it's sampling. For point field probes, you select a single point on the mesh, and if you don't have your point that you apply it to directly on your mesh lattices, it'll snap to the closest corner, essentially. What you should keep in mind is how the field vectors exist on that body cell. So let's say you put a point field probe at this corner of a body cell in your model. If you're probing electric fields, it'll be the electric fields on the lattice edges in the positive directions, will be the components. If you're probing magnetic fields, then it's at the center of those lattice faces in the positive direction. So let's say I want to probe the X component of the H field. My probe will look like it's at this corner in the mesh, but it's actually probing in the half cell in the positive Y direction and a half cell in the positive Z direction. So that's one thing to keep in mind. So exterior field probes, these can be used to obtain either electric or magnetic field data at a point location outside of your domain. So this is beneficial in that you don't have to increase the size of your domain and therefore increase the amount of time it takes to simulate to collect these far fields. And then lastly, there's the option for a 3D probe. So you can use these to visualize a variety of different values like electric field, magnetic field, electric current, or conductivity. It's similar to the animation probe, which I'll cover after this, but you can actually visualize volumes with cut planes. And the data from these can be processed either in Discovery or in ParaView. It's very easy to work with in that regard. So before I go into the animation probes, I'll cover bulk current probes. So bulk current probes measure current through a region. So it can be used to measure current through structures or through lines. The way it's calculated is using Ampere's law. So the integral of your magnetic field over some path. Magnetic fields are computed at half cell locations, as I've shown a couple times. So bulk current through a defined region is actually computed at a location half a cell in the positive normal direction from where you are seeing it being defined in your model. So kind of I'll go into a bit of like how you can define these and then some consequences. So on the right, there's 3 different examples. So you can define your bulk current probe at a point. So you can actually have your min and max definitions for your bulk current be the same. And it'll still be actually, it'll still be able to provide a current. It's just a current through a point where the the magnetic fields used to compute that are in the half cells around it. You can have 2 coplanar points that don't exist at the same location. And once again, you have the magnetic fields, which are these blue lines used to compute that go in the half cell direction, in the positive direction for each of the 2 coordinates. And then lastly, if you have like a box, so you have min, max values are different for each of your directions, X, Y, Z, you can define a skip factor to then get the bulk current at a certain number of mesh cells within that box. So in this case, it'd be the current through this plane at like every 4 cells from the min to the max if you define a skip factor of 4 or something. So one thing that you might run into with bulk current probes that can be easy to miss. Since magnetic fields are computed at half cell locations, the current that's computed is 1 half cell in the positive normal direction from where you're defining it in the model. So let's say you have a cable that steps like this with the red line. If you place your bulk current probe at location 1 right here, then the current that is going to be probing it's in the positive X direction. Let's say that's the normal that you select. It's going to be probing it half a cell in the positive. So it's actually probing on the cable. However, if you say place your bulk current probe at 0.2 here, you see in the model it's on the cable, but it's using the magnetic fields in the positive x direction, half a cell away, that don't lie on that cable. So it'll be probing current in free air. So it may look like you're probing the current on the cable, but you're not. So just be mindful of where you place these probes as well as the normal direction. So that's one thing to keep in mind. Animation probes, so those can be defined on a variety of surfaces to get a lot of data. So like you can look at electric current, normal electric field, normal magnetic field, magnetic current, things like that. They're very useful for looking at overall trends, but they really shouldn't be used if you're looking for quantitative data. And part of the reason is that in order to show a specific value for a cell, it's averaging data across several cells. So you're kind of losing some information there. So if you're looking for actual quantitative data, you should be using those field probes, the box field probe or the point probes. And then lastly, voltage probes are pretty simple. You just select 2 points in your model across which you want to measure the voltage difference. Processing results. So you can run your model in this discovery GUI, or you can run it from a command prompt on an HPC or on a cluster or something. And then it'll output probe files, kind of showing how you can process these probe files in Discovery. You can do so in like MATLAB or Python, but you can also visualize this data in Discovery. So if you right click and click plot, this is showing a voltage probe. If you right click on the plot, you can say add result and then overlay, let's say, a different voltage probe to see them on top of each other. You can do this however many times you want. But if you want to get into more complex processing, I'd recommend using something like Python. So for indirect effects of lightning, your resulting waveforms from your simulation need to go through a reduction process to convert those responses to a standardized set of waveforms and levels for verification testing. So things you'll look at would be like peak amplitude, the area under your curve, like for charge, action integral for current, rate of change, so the rate of rise, as well as frequency of oscillation. And then based on those, you can select appropriate standardized waveforms. I don't get into this too much, but these are pulling from DO160. This is an example of current waveform 1, and which is the same amplitude and waveform shape as voltage waveform 1, and also the same shape as component A. But if your response from your simulation looks like one of these, then you could say it's current waveform 1 with some sort of level. And then lastly, one thing that you will likely want to do is validate your results. For one thing, it provides confidence in the simulation, but for another thing, once you validate your model or once you validate your model, you can actually go back in and make modifications to parameters and trust that you're actually the information you're getting from that simulation matches what you'd likely see in real life. So these validations, they can be done on, say, like smaller areas, so like fuel tank ignition, or on full vehicles. We've had a lot of experience with full vehicle validation. This is just an example of a validation that was done for the simulation on transport category aircraft. This won best presentation at the conference that it was presented at. And on the bottom right, it's an example of how data can be presented for these validation efforts, where you plot like the peak value for your test data against the peak value for the simulation data for the same probe, and then look at the difference. So the red line here would be if they're identical, and then you can look at plus or minus 3 dB, plus or minus 6 dB to get an idea of the range. And at higher values, typically they should match very well. If they don't, you need to go back into your model and really look at updating parameters and making some fixes. Lower levels, in this case, they even matched at lower levels, which is impressive, but those can have a little more deviation. So general guidance for lightning. Lightning, split into two different areas. So indirect effects of lightning, and direct effects of lightning. So indirect effects of lightning is looking at the electrical transients that are induced on the systems of the vehicle given a lightning strike. Direct effects would be things like physical damage caused to structures and systems of the vehicle due to a direct attachment. This could include, like, say, fuel ignition in a fuel tank or something like that, or voltages that can develop. So why is this important when you're building your model? Well, you want to take into account what probes you want to include. So indirect effects of lightning, you'll want to be probing your harnesses, your cables. Direct effects of lightning, you'll be wanting to look at structural currents, structural voltages. So that's why that matters, is knowing the end goal of this simulation, or you can do both. Commonly, the source used is current component A, but depending on where you have your attached lines, you may be looking at current component D. But like current component A, severe environment seen in the first return stroke of lightning flash for zone 1A. I just show the details here. You can select these when you input your double exponential in your model. And then kind of just going over lightning redistribution effect. And this is important, actually. It kind of goes back to the magnetostatic scaling I mentioned before. So for that double exponential component A, it has different coupling behavior at different times in that component. And it's called the lightning distribution effect. So at early times in the waveform, it's like less than 3 microseconds, you have a high rate of change of current. And in this case, the coupling is dominated by inductance. So larger diameter or larger size of something, lower inductance, lower impedance. So the path of least inductance. So current will take the path of least impedance. So in this case, it'd be the path of least inductance would be preferred at this early phase. What this means is something may have low inductance, but a relatively high resistance. It still may be preferable to a low resistive path, like a copper shield. So in earlier times, lightning will take the path of primarily structures, even if they're more resistive. Later time, so more than like 30 microseconds. So in between, that's the transition period. At later times, which is later than 30 microseconds or so, you have relatively low rate of change of current. And so then coupling and distribution is dominated by the resistance. So in this case, you'd see a lot of current being like going on your cables rather than structures. Why this is important to take into account for your modeling would be if you're doing magnetostatic scaling to try to take advantage of this increasing time step, decreasing simulation time. You'll want to have lower rate of change for your permittivity in the earlier part of the waveform, because the earlier part of the waveform is not magnetostatic or quasi-magnetostatic, whereas you can have a higher rate of change of your epsilon value at later times when it becomes resistively dominant and magnetostatic, or essentially magnetostatic. So just a little bit more on the lightning redistribution effect. It's significant for vehicles with composite structures. It's kind of what I said before. Cables can be much less resistive than CFRP, but at early times, that CFRP can still be a more attractive path for current. ECF on composite surfaces, while really important for direct effects protection, does not significantly help for indirect effects. And ECF bulk resistivity is similar to CFRP, typically. Margins. So margins will need to be applied to your simulation data. The question is, what margin do you select? And that's actually a rather complicated question. So it's considered basically an uncertainty factor for your results. There isn't a standardized method for quantifying margins, but the best way is to perform a validation, comparing your experimental results to your simulated results for a particular vehicle. And one thing that can get kind of complicated is you can maybe even have like a sliding margin based on amplitude. So have a smaller margin at higher amplitudes where they tend to match very well, and a larger margin for lower amplitudes where you may see more deviation. In the absence of validation, a commonly used margin is 6 dB or a factor of 2. This is common in aviation industry and has been verified on numerous programs that we've worked on. So when you apply this margin, essentially, you would take all of your simulation values, or all of your actual transient levels, so the data you collect from your simulation, multiply it by a factor of 2, and then use that value for assigning your equipment test, or your ETDLs, or equipment test design levels. So the DO160 levels that I kind of mentioned before with the waveform reduction. So these simulation ATLs, after you apply a margin, can be assigned that DO160 lightning test category. These test categories consist of a standard test waveform and a test level that's based on amplitude. I don't go into much detail here, but there are 7 standard test waveforms, so 1, 2, 3, 4, 5A, 5B, and waveform 6. Which one is applicable depends on if you're looking at voltage or current transients. For sources using lightning components A or D, the most common transients that you'll see are typically waveforms 1 and 4, so an earlier peak, or waveforms 5A, 5B, so a later peak, later decay. For sources using lightning component H, waveforms 3 and 6 are more commonly observed. This is just a repeat of what I showed before, just an example of these standard waveforms. So lastly, for lightning, I just want to go into some suggested parameters, because it can be really hard when you're starting these models, especially if you haven't done them before, knowing what exactly to pick. So if you have a smaller vehicle, so something that maybe like 2 people would be in, you may choose like a 1-inch mesh. And in this case, I typically, so 1 inch or 25 millimeters. And then for the buffer space between your geometry and domain boundary on each domain face, I typically go for about 150 cells. So in this case, it would be 150 inches. That kind of depends on, that's not a hard and fast rule. So if you want to go with more, you can go with more. If you think you can get away with less, you could give it a shot. The time step size that I like to use is 4 E-11, or and then also an end time step of 500 microseconds. And then for a large vehicle, so something that would be like a transport category aircraft, you'll likely have to use a lattice step size of 2 inches or 50 millimeters. I typically go with a similar buffer space, about 150 cells. Because of that larger step size, you actually can have a higher time step size, so 8 E-11. And then sometimes these can take a long time to simulate, and you can maybe only run your simulation out to 400 microseconds. I wouldn't recommend doing less than that. If you can get to 500, that's great. Your time step increment method for lightning, you can do magnetostatic. I just give some example parameters that you can use here. Your boundary condition, you'll want to go with your MER1 H field. That's an absorbing boundary condition, but it allows for materials to intersect that boundary, which you'll need because you'll need to have your attach and detach lines. So your attach location will determine what source you use. So for lightning zones 1A, 1B, which are your first return stroke zones, you'll use lightning component A. For lightning zones 2A, 2B, your swept stroke zone, you'll use lightning component D, which is the same shape as component A, but a reduced amplitude. For your source geometry, you create a line from your vehicle to your domain boundary, and then you assign a current excitation source with that waveform, whether it's component A or D. For your detached geometry, you do a line from your vehicle where you want your detach to occur to the domain boundary and assign a PEC material, or perfect electric conductor. For cable harnesses and probes, typically you'll be looking at open circuit voltage and short circuit current. So depending on that, your pin resistance will vary. You want to have low frequency approximation on in your harness settings to ensure that you are accurately capturing coupling to the interior conductors. You can have skin depth effects off. Outermost shield termination resistance, typically you'll go with 2.5 milliohms. Inner shield termination resistance, I go with like a micro ohm. And then pin terminations, if you have open circuit voltage, typically I like to use a micro ohm and a mega ohm. And then you probe voltage at the mega ohm side. Micro ohm for short circuit current, you could go with 0 ohms. And you can probe current on any point on the line for short circuit current. And for volt current probe locations, I typically, once again, I recommend probing at each connector. So on both sides of a bulkhead at each LRU. And then some just parameters if you don't know kind of what you're dealing with in terms of bonds or materials. So on the left, I just give some examples like CFRP. If that's all you know you don't have information about the plies, you don't have test results, you could just go with something like 1E4 in the meantime. aluminum, titanium, ECF. Dielectrics you can exclude from your simulation for the most part. For lightning, they're effectively transparent. They're not going to conduct current. So those can be excluded. Seams and joints and bonding can be kind of complicated. You're looking at different materials. So you have like CFRP to CFRP, CFRP to metal, metal to metal. And then you don't know, is it going to be a good bond, a moderate bond, a poor bond? Like, is it being planned? Like, is the plan to use it as grounding? That'll determine it. And even then, like, let's say you have a CFRP to metal structural bond, you know it's not going to be great. What's not great? It could be anywhere from 1 ohm meter to maybe 100 ohm meters. This is when sensitivity analyses can be really helpful, is seeing, does this joint really impact my transients or not? Like, how well does this need to be characterized? But overall, if we're looking at like good bonds for CFRP, maybe a milliohm meter, moderate 10 to 100 milliohm meters, and poor would be on the order of ohms or higher. Metal to metal, just low values. Hinges are complicated. They can be decent on like the 10 milliohm range, or they can be very poor on the order of kilo ohms. Bond straps, they can vary. You can also look at individual fastener resistances and then try to create like an overall parallel resistance for your seam. So if you know the number of fasteners that you have in a seam, you can assume some sort of fastener resistance and then calculate what would be the parallel resistance across that joint, given that number of the number of fasteners and the fastener resistance. If you have things like dielectric seals, you can use an infinite resistance, or you can use a physical gap in the model. Sometimes one's easier than the other. General guidance for HERF. So HERF, also called external EME or electromagnetic environment, simulations can be used to look at internal coupling. So HERF, which is high intensity radiated fields, are environments that will penetrate or interact with aircraft to establish an internal RF environment. So electrical and electronic systems will be exposed to this internal RF environment. What develops internally is affected by apertures, your seams, your bonding, aircraft resonances, any lossy materials you might have in cavities or in your vehicle, so like plastics and stuff. Simulation can be used to look at coupling from fields to cable bundles, so your LLSC, low-level swept current. Create transfer functions for field penetration, so LLSF, low-level swept fields. And this can include statistical post-processing of regional field data, and then also H-field transfer functions, so LLDD, low-level direct drive. So you can look at surface currents and generate transfer functions. Just a quick overview. LLSF is attenuation that the aircraft provides. And this is looking at like 100 megahertz to 18 gigahertz. LLSC is current induced on the wire bundles. And so this would be from like 10 kilohertz up to 400 megahertz. The measured attenuation and current transfer functions are combined with your environment. Your environment will depend on your vehicle type and severity, and then you can use that to determine internal environment. So software is well suited to perform these simulations up to 400 megahertz. I'd actually push that even higher. You can create submodels if you want to go as high as 18 gigahertz, but full vehicles can be very difficult to achieve 18 gigahertz because the higher your frequency, the lower your cell size that you can use in order to get those 10 cells per wavelength. What's beneficial about these sorts of models, though, is they can be used across a lot of different applications in E3. So you can use the same model for lightning as you use for EMP, as you use for HERF. In certain applications, like maybe EMC or P-static. So the benefit is there's a lot of development time up front to create the model, but then it's just a matter of changing your probes and sources after that to look at these different environments. Simulation is beneficial because you can also expand on what you're testing. So let's say if you like miss a test point in testing, but it's like your simulation's well validated, you can go into the simulation and say, let's look at what the fields are in this location. And have some confidence that it's accurate. For LLSF or low-level swept fields, you would use the boxed region field probes to replicate where you're putting or where you're probing in test. You can look at the min, max, and then also compute average fields within that boxed region and apply 5% bandwidth averaging to smooth the data. LLSC, low-level swept currents, you'll want to measure bundle currents 2 inches away from box connections or whatever location is being used for testing, and use octave envelope in your post-processing to set test levels. Yeah, so as mentioned before, like let's say you missed a bundle current in testing, you can go back in and look at what it is in simulation, or you can also re-simulate after aircraft modifications are made. Some important things to keep in mind when you're simulating HERF would be accurate harness resistances. So it's important that you have the correct number and types of cables and shields, as well as like the shield resistances. Overbraids can be very important in determining cable bundle resistance. Termination impedances should also be accurately reflected. And then in terms of geometry, you want to make sure that you accurately model the structural geometry with material properties as well as loss mechanisms, so maybe including some dielectrics. Yeah, different aircraft regions can produce different responses for a cable based on the surrounding geometry. So you want to make sure you're accurately capturing apertures and materials. So in terms of harnesses, it's important that you capture as many harnesses as you can, essentially, as well as parallel conductors. So harnesses that are surrounded by a lot of parallel structures or other harnesses will receive some amount of shielding. And so you want to make sure that you can capture that effect, as well as proper routing, so including macro and micro branching. So more harness branches tends to lead to greater destruction of modes on those cables and overall reduce bundle current levels, sometimes by as much as 20 decibels. And then also, if validating your simulations, once again, make sure you place your probes in the same locations in the mesh as what was used for tests. And then finally, you'll want to make sure that you are accurately accounting for frequency-dependent impedance for your harness conductors. And then this is just kind of showing that complexity of harnesses can impact the coupling response for a HERF environment. So multiple conductors, how those conductors are packed in your harness, and then harness branching. So those can all help to or contribute to reduction in coupling levels as well as energy dissipation times. So you can simulate LLSF and LLSC on a full like transport category aircraft. You'd use a broadband Gaussian source, or a broadband Gaussian pulse as your plane wave source. You could use one of the HERF environments that are defined, but using a broadband, just a basic Gaussian pulse, you can define transfer functions, which I'll go into. You want to make sure you use multiple plane wave orientations to really well characterize the impact of the HERF environment. And then also you can probe surface current density using an animation probe to look at basically what surface currents develop. Or you can look at normal E-fields. So in this case, it's interesting to see like what E-fields develop inside of the aircraft. How does the floor impact that? You can actually see a bulkhead right here. So that can be good for overall visualization. Electric fields. So for LLSF, electric fields are measured in areas of interest in the model using box region field probes. Basically in the same locations that antennas would be placed in testing. So what you do is do a cube or so with length maybe 4 to 6 inches on each side. And then you'd want to collect, once you have your data from simulation, you want to compute the minimum, maximum, and average electric field across all points. The average is typically what you'll be using, but it can be helpful to have an idea of maybe like the total range, min to max. The reason you'd want to use the average is test horn antennas typically average fields over some spatial region, so you want to do that in the simulation as well to provide a better approximation, rather than looking at the field at a single point where you may have you know, some increase or decrease in field that maybe for the whole region you wouldn't necessarily see. You might be misled, essentially. And then finally, you can apply a 5% running bandwidth average. For LLSC or the cable, like low-level swept current, the cable responses, bundle currents are typically measured 2 inches away from box terminations. These bundle currents can be normalized by your incident field. So when I was saying you can use your basic Gaussian pulse, like a generic Gaussian pulse rather than a HERF environment, you can normalize the responses on your cables by that Gaussian pulse. And then I think I mentioned this in a later slide, but then you can apply this transfer function to your different environments. So you can say, I want to look at like HERF environment 1, and then apply your transfer function to that environment to see if I had used that environment as my source, what would my responses be? You can probe magnetic field at points near the skin to look at skin currents. These would be similar to like a B-dot probe. So this would just be a point field probe. You want to make sure that you keep in mind, once again, I try to constantly mention this, but what your lattice looks like. So where are E fields on your FTTD cell, and where are the magnetic fields? And so when you put a point probe, and like let's say you're looking at the top skin, like the upper skin for the wing, positive Z direction would be above the skin. You want to put your point probe on the mesh for the skin, and that would get it half a cell in the positive direction. So the E fields, or sorry, the magnetic fields just above the skin. If you're looking at currents on the lower skin, you'd want to actually put it 1 cell beneath the mesh of the skin to get it half a cell away from the skin, essentially. So that's just one thing to keep in mind, once again, is how the mesh can impact where you place your probes. For 18 gigahertz simulation, so that higher range of the LLSF, it very much is not practical to resolve a full aircraft. And so what you can do is actually section your aircraft into different areas or different cavities to capture important coupling characteristics. So in this case, I looked at the cockpit of an airplane, and that's all I modeled for 18 gigahertz. So that way I could have that reduced cell size. It wouldn't take months to simulate, and I could see what the response is up to 18 gigahertz. So similar to Lightning, I just kind of give some suggested parameters for your simulations for HERF. If you're looking at an LLSF simulation, then your minimum frequency you want to be about 100 megahertz, maximum frequency maybe 18. Once again, 10 cells per wavelength at the max frequency. That would come out to 1.67 millimeters or 0.065 inches as your cell size. For low-level swept current, minimum frequency 10 kilohertz, maximum frequency 400 megahertz at 10 cells per wavelength. That would be like 3 inches for your mesh size. Let's say you want to do a combined one. You wouldn't be able to capture the lower range of LLSC or the upper range of LLSF, but you might be able to do something like 1 megahertz to 1.2 gigahertz. This would be for like a 1-inch mesh, which is a typical mesh for like a smaller vehicle for Lightning. So if you're just taking a Lightning vehicle and going with HERF, that might be the range you can do. I tend to recommend a buffer space of at least 10 cells from your domain to your materials. Technically, the minimum is 3 based on where that Huygens surface for your plane wave exists, but I like to have a bit more buffer space personally. Time step size will be dependent on your step size for your lattice. Your end time, you want to make sure it's 1 decade lower than your min frequency. So basically, your minimum frequency then versus that would be what the simulation will tell you in the domain as the end time that you should use. Do 10 times longer than that so that you can get enough data at that lower frequency to be useful. Your increment method for your time step should be constant, not magnetostatic. Your boundary condition is PML because you won't have materials that are intersecting that boundary. You can go with the perfectly matched layer boundary condition. Source type, plane wave, and then the default Gaussian that when you create a plane wave in the model, it'll populate it with a default Gaussian based on your min max frequencies in your domain. That tends to be a good enough input for that source. Pin configuration. A lot of the times I'm starting with a Lightning model, so I'll keep like open circuit voltage, but turn off low frequency approximation for your harnesses. Otherwise, you will not get accurate results. One thing you'll want to do is turn on skin depth effects. That's an option when you're defining your cables, where you define like the conductivity, the thickness. That's important to take into account for these simulations. And then once again, just outermost shield termination resistance, typically 2.5 milliohms. If you have an inner shield, maybe like a micro ohm, and then pin termination resistances. If you're doing VOC, micro ohm and mega ohm. You really are only probing bulk currents though, so 2 inches or 50 millimeters from each box termination. And then these are the same parameters for materials and joints, as I showed for lightning. And then quickly, before we move into Q&A, I just want to show basically how this can be applied to a different model. So that was a lot of stuff about airplanes. Let's look at a car. And then also different applications. So like, let's say you're curious about radiated emissions or radiated immunity. So you start with the car, and you want to model noisy components in the power conversion process. So you get the original manufacturing CAD. You go through your simplification methods that we kind of covered for like an airplane to get this surface representation of the car. And then you want to get your cable center line or your harness center lines for cable lines. And then you want to assign your cable parameters or your cables to those lines, or import a KBL file. So this is for this model as an example, just the harnesses that were used. And then yeah, you can use KBL imports for faster pre-processing, so for inputting of these cables. So for radiated immunity as an example, you can illuminate the car to determine the shielding effectiveness of the structures and the materials. And then you can probe transients that couple to the harnesses and the equipment on the inside. The same model can be used for radiated emissions, just different probe and sources. For radiated emissions, this is an animation of the electric field, normal electric field, and you can see where it starts on the cable, kind of bounces around, and then you can see basically the field amplitude, where it's highest, and what it looks like on the outside. The emissions profile, so electric fields can be probed any distance from the platform. So if you remember that even if your domain is smaller than where you want to probe, you can probe fields further out from your domain. One benefit of knowing the emissions profile early on in this design process is it can influence the design before you get into that expensive prototyping and construction phase. So you can also, suggest mitigation techniques or identify noisy components that may need more work. And then this would be a case where you have a field coming in from the exterior and looking at how it couples to the interior. So something like chassis shielding effectiveness. So you place bulk current, or not bulk current, so you place a boxed region field probe inside your vehicle, and then look at what fields develop from that exterior source. Similarly, same source, you can look at coupling to the cables and see what the transients are induced on the cable to electronic unit interfaces. Compare those to thresholds for your electronic units, and then determine if you need mitigation. So you can look at maybe what shielding can be added or changed, or maybe different cable routing, and that can be investigated with the simulation. So yeah, that's it for the slides, and I figure we can move into Q&A now.
Thanks so much, Megan. That was great. Right now, it looks like we only have one question, so I can read that to you, and then we can maybe hang out for a few minutes in case anyone else has other stuff that they want to post into the Q&A. But the question that I'm seeing here is asking, can you elaborate on the physical meaning of seam/joint impedance and how it is incorporated into electromagnetic models?
Yeah, so I guess the physical meaning would be you have like your different fastener stack ups and like kind of like how that seam is built in reality. So you have your let's say like your surface to surface, you have some sort of RLC component to that, and then you have your fasteners that then like connect those surfaces. So you can think about all the different paths that say current can take, and that can be reduced down to like say an overall if you go from one side of your panel to the other, rather than looking at the electromagnetic effects of each of those individual parts of your joint. So from each fastener or from that surface connection, it can be combined into a single like RLC circuit with an effective like resistance, inductance, capacitance. Hopefully that answers your question.
Sounds great.
But if not, you can just ask in the chat and I can follow up later with a more detailed written response if that helps.
And as we mentioned, we'll hang out for a few minutes, but in case there are people who don't have more questions, thank you very much for attending. Following today's webinar, everyone who registered will receive an email from EMA with a link to the recording of this presentation. I know that also came up in the Q&A. If you have questions about a particular section of interest after you log off, please feel free to reach out either through our website, ema3d.com, or via email. Next up in our Expo sessions, look forward to the upcoming Radiation Hardening and Spacecraft Charging Masters Workshop. It's another no-cost virtual event, including several training workshops and technical discussions. It'll begin tomorrow, the 26th, at 11 a.m. Eastern. So thank you very much for your time and attention, and have a great rest of your day. And again, we'll hang out here if more questions do come up.
I think I see a few of them in the Q&A. Will the slides be shared? Yes, we can. Let's see. When defining a spatial gap in the model, is it standard practice to represent it using a seam impedance with a sufficiently high resistance value as opposed to modeling the discontinuity purely through mesh resolution? Yes, it is standard to use a seam impedance. And that's something where if you have a mesh larger than what could be used to basically model that that gap or those details, you can use them that seam impedance. I do that a lot. When processing CAD data into simplified model, does this tend to be done in CAD software or done in the EMC modeling tool itself? That can be done in Discovery, so in EMC Plus. You could do processing prior, like in whatever CAD tool you have, but it's Discovery is more than capable of handling that, and that's usually how I do my models. Let's see. How to decide step size in the domain for larger CAD models so that there's less computation time. So this will depend on you know, the frequency that you're concerned with. Will limit kind of like how big a step size you can use. It can be kind of, so some things to take into account would be details that you can resolve. So obviously the higher your step size, you can't really resolve as many details. So it's dependent on the frequency content of your source, how much, like the size of the objects you need to resolve, and then also it can also depend on, I mentioned the frequency content of your source. Like if you have a higher frequency source, you may actually need to go with a smaller mesh size. In doing so, I didn't mention this in the slides, but one way to look at what sort of mesh size you need would be simulating, like say your plane wave in an empty domain and making sure that the responses you're getting for your fields are what your source is supposed to be. If your mesh cell size is too big, you'll see some distortions. But yeah, it can sometimes be challenging to figure out the exact cell size you need, which is why I wanted to provide those kind of rules of thumb. Would be like, you know, 1 inch or 2 inch for lightning curve. Let's see. Can we design 50 Hertz power transmission lines using A, cables, or B, applying current source to transmission line CAD model? Which one is convenient? Cables or by applying current source to transmission line CAD model? Which one is convenient? I guess you could do either. I follow up on that one with more details though. I think that's all the questions I see on my end, at least. And yeah, once again, if I didn't answer your question or if you want more detail, yeah, feel free to message us or you can email and we can get back to you.
Sounds great. Well, thank you very much for catching those, Megan, and for your responses. And if we don't see any more questions in the chat, I think it's safe to conclude and hope that we see you all in our subsequent webinars and presentations.
Thank you for attending.